Hey, good morning, everyone. So while we're still waiting for others to join us, so we probably can start to give a little or brief introduction of today's speaker, Dr. Zhang. And Dr. Qingpeng Zhang is an associate professor with the School of Data Science at the University of Hong Kong, City University of Hong Kong. And before that, he was with the Department of System Engineering and Engineering Management as affiliate member, and still be an affiliate member now. Before he joined the City University of Hong Kong, he worked as postdoc research associate with the Tessel's World Constellation Department of Computer Science at Ruslan Polytechnic Institute. He received the bachelor degree in automation from Huazhong University of Science and Technology in 2009, and the PhD in the System and Industry in Engineering from the University of Arizona in 2012. His research interests include healthcare data analysis, medical informatics, network science, and social computing. So today he will bring us the talk about the knowledge-based aware suicide risk prediction. So thank you very much, and I put the turn to Dr. Zhang for his talk. Thank you.
Thank you very much for the introduction, Professor Zhang. Good morning, everyone. Although it is late night here in Hong Kong, it is a great pleasure to be here to present my research related to knowledge-enhanced machine learning models for suicide risk predictions. I worked with Professor Xiaoming Li for quite a number of years on a number of papers, mostly on HIV predictions and HIV interventions. And here, today's topic is mostly the outcome with the collaboration of my former PhD students, Dr. Zhongzhi Xu, and the collaborator, Professor Paul Yip, in the University of Hong Kong. So Dr. Xu is now a fellow in Hong Kong U after graduation. A very brief introduction to our university. It's a City University of Hong Kong. It's one of the state government or public universities in Hong Kong. It's quite small in terms of the size, physical size, but it's actually very huge in terms of number of students and the research performance. We're constantly ranking about top 50 in those QS ranking and Times ranking. And my school is a new school at CTU. It was established 3 years ago, and it is the first standing alone school in data science in Hong Kong and in the region, in this Greater Bay area in southern China. And we have professors from multiple disciplines, with those from mathematics all the way to very applied researchers in different fields, like in smart cities, in green energy, in healthcare, and in fintech and others. So we have 2 undergraduate programs and the postgraduate programs, including master and PhD programs. Okay, and my research group at Hong Kong, at CTU, we mostly work on health informatics, medical informatics research, but we focus on using networks to do research. So that includes the analysis and the modeling of networks, as well as how we can construct networks and use it for machine learning tasks. So for example, the network on the left, this is the Comorbidity Network that we are going to use to predict the suicide and self-harm incidence for individual patients. And on the right, this is another mental health related social network that we constructed using the online social support exchanges among depression patients in China. So today, I plan to talk about 2 papers or 2 topics. The first topic is to predict the post-discharge self-harm incidents using disease comorbidity network. And also we'll talk about some simple extensions of the model we introduced here. And then I will spend less time on introducing the prediction of suicide risk using knowledge graphs on social media. Okay, so the first topic, we try to use disease comorbidity network to predict the self-harm and suicide cases in Hong Kong. The reason, the rationality of using the comorbidity or co-occurring patterns of different diseases is that we are seeing increasing evidence that we need to combine different risk factors in terms of getting a better understanding of the suicide and self-harm risks. So in general, the background is self-harm and suicide. Those kind of behaviors are preventable, or the majority of those incidents are preventable if the risk can be identified early. But existing risk prediction models mostly concentrate on the main effects of medical diagnosis to determine self-harm or suicide risk. So for example, last year, like in January 2020, there was a paper, or 2019, I forgot the exact date, there was a paper on JAMA Psychiatry indicating that the cancer patients has a higher chance to kill him or herself, which is expected, right? And we have quite a lot of these studies in the literature indicating that patients with a single disease would have a higher chance to commit suicide or self-harm, right? But recently, there are more and more evidence showing that the co-occurrence of multiple diseases is actually related to self-harm risk in a different way from the simply adding up the main effects of individual diseases. So in psychiatry community, so there is a call for combining risk factors. So there are some examples. So why combining those risk factors cannot be well modeled by simply adding up the risk score that we can learn from, say, logistic regression, right? So in some cases, if a person got two diseases, and you can imagine that there are many diseases that always co-occur, right? If a person got A, so this person will very likely get a disease B as well. So the case of getting this both A and B basically indicate that this person get A. So it's not actually reasonable to just sum up the risk score or associated with A and B, because in that way we overestimate the risk, right? But in some other cases, the existence of disease A and disease B actually could indicate a much higher chance or much higher risk for committing suicides. And there could be multiple reasons for that. There are some evidence about these biological processes that actually lead to the increased risk for committing suicides if with multiple diseases. And also sometimes there are also behavior factors that actually lead to a higher risk if two or more diseases are acquired by the patients. So in this way, if we just add up the risk score associated with these two diseases, we underestimated the risk. And also there are some literatures indicating that the sequence of acquiring different diseases also matters. So you can imagine that if there's a long-term cancer patient and acquire another disease, so it may not change change the risk too much. But if we reverse the sequence, if it is a long-term patient, say for hypertension, and then acquire a cancer, so in that, so if we reverse this sequence, the later case actually indicate a much higher chance of committing suicide and self-harm, right? So What we try to argue is that combining different risk factors is more complicated than a single logistic regression model can capture. And we have to consider the sequence of acquiring different diseases. Okay, so people might argue that traditional regression models can also introduce, say, pairwise interactions to address this issue, right? If it's a very simple linear model, linear regression models with only independent, with the summation of multiple independent predictors or independent variables, right? So of course that was not ideal, but for regression models we can add up some pairwise interactions or even triple-wise interactions. However, this approach is still quite limited because for one thing, the pairwise interactions are usually difficult to predefine, right? For those logistic regressions, we have to predefine those pairwise interactions, particularly when there are many correlates. And second, the complex interactions between characteristics of multiple diseases may go beyond pairwise interactions. It could be triple-wise interactions or even higher order. And also it is quite computational expensive. Later we will see an example. So here we try to utilize a network medicine approach. So we utilize the structure of the whole network and try to extract features from the network directly instead of explicitly defining those interactions using a linear model. So in this study, to address the complex, potentially multiplicative effects of multiple diagnoses on self-harm risk, we proposed the disease comorbidity network to enhance the effectiveness of risk prediction for self-harm. So here, the comorbidity network refers to the existing knowledge of the frequency of the co-occurrence of multiple diseases. So we hypothesize that incorporating the comorbidity network information can improve the accuracy of self-harm prediction. So this is the comorbidity network that we constructed using 7 years EHR data from HA. So HA represents hospital authority. So in Hong Kong, the majority of the patients they go to public hospitals. So we have 44 public hospitals. So hospital authority is organizing all those hospitals. So they are sharing the same databases. So essentially, we have a territory-wide data for 11 years, and we used the first 7 years to construct this comorbidity network. And then we try to learn information from this network and then predict the suicide cases for the following 4 years. And this network, we have 938 nodes. Each node represents a small family or small group of diseases. So for example, it could be representing type 2 diabetes. And you know that in ICD code, we can further have further resolutions like multiple variants of type 2 diabetes. But that will make the network too large, too sparse, and too complicated. So here, because we are essentially predicting the self-harm, instead of predicting all the different variants of self-harm, so we aggregated based on the ICD code. So essentially, we have 938 nodes representing these over 900 small groups of diseases, and connecting them are over 15,000 weighted edges. So the edge actually represents the co-occurrence between those two diseases. Okay, so in general, I mean, this network is very general because we didn't retrieve this data just for mental health research. So we have every inpatients in Hong Kong. So it covers all kinds of diseases. And here the different colors represents the higher level categories of those diseases. So here I use this to predict self-harm and suicides, and later we use it for many other disease predictions as well. Okay, and here are the subjects. We have, in general, we have over 9,000 self-harm individuals. We exclude those who didn't have any prior admission records, because in that sense, we don't have any data to predict those cases. And we also excluded some very rare cases, like some very young kids, less than 10 years old. And with a ratio of 1 to 20, we have over 46,000 counterparts, and then we split it into training sets and test set. So we use the training set to train the model and use the test set to evaluate the accuracy of the prediction model. So the model, we call it a DEX2VECT. It essentially represents diagnoses to vectors. So it basically, we try to represent simultaneously, first, the diagnosis, and second, the comorbidity patterns among different diagnoses. And then the third, the temporal patterns of historical inpatient admissions for each patient as a low. So we try to represent those three types of information as a low dimensional feature vector. So why we call it a low dimensional feature vector? Because essentially eventually we have 64 dimensions. It doesn't sound very low dimensionality, right? But as compared to the origin dimensionality of the network, it is actually much lower. So for example, in this original network, we have over 900 nodes. So if we calculate the possible combinations, the pairwise combinations, we are talking about over 400,000 possible pairwise combinations, pairwise interactions. And if we talk about triplewise interactions, we're talking about over 100 million potential triplewise interactions. So that is simply too much for a computer to exhaustively analyze it. So here we try to translate all these very high dimensionality into a low dimensional vector while still preserving the critical information hidden in patients' historical EHR data. So this is the general general framework of the model. First, for this comorbidity network, that's a nice visualization, we try to learn a low dimensional representation of each disease. So this feature vector, the learned feature vector, for example, for disease ICD-303, we learn such a vector. Okay, so for each disease, its position in the comorbidity network has been translated into a feature vector. And all those feature vectors, they share the same dimensionality. It could be, say, 2, 4, 8, 64, 128. Okay, and although it cannot fully capture the whole network information, but this low dimensional feature vector still preserves the most important topological positions of those nodes in the original network. Okay, later I will show you some examples. And okay, and for each admission record, okay, a patient may get multiple diagnoses, right? So here we have a max pooling scheme to combine, to integrate the multiple diagnoses within the same admission record of the same patient. So we combine them together into a single feature vector, which represents the comorbidity patterns of multiple diseases in this specific admission record. Okay, and then as I said before, the sequence also matters. So we have to consider a sequence of admission records of the same patient. So in that sense, we use the long short-term memory, which is just a deep learning module, which considers the sequence input. So say this is the first admission records of the patient, and this is the second admissions of this patient, and this is the third admission records of the same patient. So we use the LSTM module to combine them together, which represents the sequence of acquiring those different diseases in the past. So eventually, for each patient, we can create a personalized feature vector. So we call it the dex-to-vect embedding. So this embedded feature vector represents the different diagnoses in the past, represent the comorbidity patterns of different diagnoses in the past, and also the sequence of acquiring different diseases. Okay, and then we have additional predictors for the first part is just the original diagnosis. Second part is the age and also the gender. So this is basically all the data we have. We didn't have the lab reports for this study, and combining so those are just like the traditional the independent variables in regression models, and different different dimensions in a dex-to-vect embedding represents the latent features. So basically, we're, for example, if we have two dimensionality here, so we have two latent features from the embedding plus the other features. So we combine those features together, and then we can use like logistic regression or deep learning or SVM or whatever classifiers to give a final output of the risk of this person to commit self-harm or suicide within 12 months after discharge from the hospital. Okay, so you can imagine that the use of this model is like for each patient, when they got discharged, the model can automatically give a risk assessment score and to inform the healthcare professionals the risk of committing self-harm within a year, and it can indicate that we probably want to have some follow-up for some of these high-risk patients. Okay, and here I use three-dimensionality to try to illustrate the idea behind this model. As I said before, here we try to translate the very complicated network structure into a lower dimensionality, a lower dimensional feature vector. So in the model, we use 64 dimensions, but 64 dimensions are difficult to visualize. So here we had a simpler model with only 3 dimensions in the feature space. So you can see that here for those 3 different types of diseases, and this is the disease embedding on the left, the figure A. Okay, so you can see that in general, similar diseases, they are close to each other in the embedded space. Okay, so their distance among those different diseases actually represents the topological distance in the original comorbidity network. So you can see that still similar diseases, they are topologically, they are also very close to each other. So we basically translate that into only 3 dimensions so that you can still capture such grouping effect of different types of diseases. Okay, and on the right, this is the dex-to-vect embedding of different patients. Okay, so remember that here it only has 3 dimensions, and we haven't used it for like machine learning models, downstream machine learning models. But you can see that still in this 3-dimensional space, we can largely differentiate the red triangles from the green, from the blue circles. So here, red triangles represent the patients who engaged in self-harm within 12 months. And the blue circles represent the patients with no self-harm record within 12 months. So you can see that we differentiate quite many of them, but there are still quite a lot. They are intertwined together. So this is largely because here we only use 3 dimensions to try to model it. And if we increase the dimensionality, you have better prediction power, but we cannot easily visualize it in the PowerPoints. So To evaluate the prediction accuracy, we use 5 different metrics. The first one is AUC of the ROC curve, or C statistic. So it is the widely used metrics, but because here we identify that the prediction of the negative cases, the prediction of those who didn't commit self-harm is actually very easy. So, and also the majority of the patients, they didn't commit self-harm or suicide in the data. So it was not really difficult to achieve a very high C statistic, right? Because the majority of them, they didn't have committed suicide. They didn't have such behavior. So only use C statistic or AOC is not quite fair. So that's why we further adopt the precision and the sensitivity. So sensitivity is basically recall, okay? Because, as I said, the majority of the patients, the predicting the negative cases isn't really difficult. So we focus on the prediction accuracy of the positive cases. So we focus on whether we can capture those patients who committed self-harm or suicide within 12 months. So that's why we further split the precision to the precision of the negative cases and the precision of the positive cases. So precision of positive cases basically indicates that among all the positive cases that we predict, what is the chance of them to be indeed positive? Okay, so this is the precision of the positive cases. And for sensitivity, we also split it to negative and the positive. So sensitivity or recall basically measures the coverage of the prediction. So that means among all the patients who committed self-harm, how much of them were actually captured by the model. Okay, so that's why I highlighted this metric, because this is the thing that we care the most. We want to increase the coverage because of the very severe consequence of committing suicide and self-harm. And here is the results. We basically compare it with the baseline deep learning model. Of course, we can also compare it with the logistic regressions and other statistical models, but the accuracy gap is too huge. So here we only consider compare it to a baseline deep learning model. So you can see that in terms of C statistic, even a baseline model can achieve a value of 0.85, and which is slightly lower than our proposed model, which is almost the 0.9. Okay, so the high value of this statistic was because of the accurate prediction of the negative cases. So you can see that here for the negative cases, both the baseline deep learning models and the proposed models can very accurately predict them. So this is not quite unexpected, right? So we focus on those who actually committed self-harm. So for committed self-harm one, the precision was only improved a little bit. So here 0.54, that means among all the positive predictions, we have false alarms up to 46%. Okay, so this our model didn't improve this too much, only 1% improvement, but the real difference comes at the coverage of the positive cases. So we try to cover as many as possible, right? So we improve the coverage from 65% to over 70%, 72%. Okay, so this is the general numerical results. And we can also extract the crucial or critical risk factors that are predictive of self-harm and suicide within a year. So you can see that the number one is, of course, the existing suicide and self-harm behaviors, right? And the others are some about substance abuse, some about alcohol, some about drugs, and others. And this is the top 100 diagnoses that are most predictive of self-harm. So to summarize, we can largely cluster those risk factors into 3 distinct categories. The first one, of course, is about those mental disorders. And second is the previous self-harm behaviors using different methods, right, poisoning and others. And the third category is the diagnosis that might be underdiagnosed, because we find quite a lot that we talk to the social workers, and they told us that something, for example, some drug-related diagnosis, it could be the result of self-harm, but were misdiagnosed as simply drug misuse or others. Okay, so in general, it is similar to the previous clinical study in different countries. And we also observe some diagnoses that have rarely been reported in the previous studies. For example, ICD 986, it is the toxic effect of carbon monoxide. So this is related to the popularity of charcoal burning suicide attempts in Hong Kong. And in general, in Eastern Asia, we have been seeing an increasing rate of using charcoal burning to kill themselves. And we can, as we work on the network, so we can further extract the comorbid diagnosed patterns. So what are the pairs of diagnoses that are most predictive of self-harm? So here, this is the top 10 pairs of diagnosis. So without too much surprise, most of these top ranked pairs comes with the prior self-harm attempt, which is E950, right? But surprisingly, we also identify quite a few of those pairs of diagnoses that were not the prior self-harm attempts. So you can see that here we have this 292 and 305. So if a person got these 2 diagnoses together, the chance of committing self-harm and suicide is even higher than other patients who have already did self-harm before. So this is something really exciting. So this is the top 100 pairs. So we have quite a lot of such pairs of diagnosis that could lead to a higher risk for self-harm than the prior self-harm record. So to summarize, most of those pairwise, those pairs of diagnoses, they involve previous self-harm records, E950. But for some others, for example, if a patient has both 292, which is drug-induced mental disorders, as well as 305, which is the non-dependent abuse of drugs, so both about drugs, and his or her risk for self-harm was even higher than many patients with previous self-harm record. So this indicates that substance abuse in Hong Kong was a major concern, especially among the young people for the period of study in this territory. So there are many such observations which represent some helpful insights for clinicians and the frontline researchers and healthcare professionals to design some new social science or behavioral health studies regarding those self-harm preventions. Okay, so to summarize the whole study of this text-to-vector model, so the model can identify 72% of all the inpatients at risk for self-harm within 12 months with a 54 precision. So because the coverage is already over 70%, so it indicates some sort of usability in screening practice. So we do not intend to replace real humans or real doctors and nurses, but it can act as an AI gatekeeper, right? So because at this moment, when we discharge those patients, we never consider the likelihood of those patients to commit self-harm. But if we can implement this in the hospital, at least for those patients with certain risk, so we probably can provide like brochures or some follow-up phone calls, hotlines, services, or others to try to reduce the chance of the self-harm and suicides of those patients. So the strengths of this model is that first, it incorporates the full comorbidity patterns into the model. And second, it considers simultaneously the diagnosis, the comorbidity patterns, and the temporal patterns of the historical admissions. And more importantly, this model is really generic, so we can apply it to any other diseases. So the only thing we have to change is to change the outcome from E950 to other outcomes, the other ICD codes. Okay, so the full paper is here. If you're interested, you can check out the full paper for technical details. So we also extend this model to interpretable machine learning models, because previously that DAX2-VEC model, although I mean we translate the network structure into the low-dimensional feature space, right? But basically we didn't know how it was done, and because here we are dealing with healthcare medical problems, especially this is self-harm. So if without any interpretations of how the predictions were made, the model cannot be adopted by the frontline professionals. So here we changed the modeling approach. We are still working on the comorbidity network, but we try to propose an interpretable machine learning models here. So the full paper will come out like in next week. It was accepted, and we have a shorter conference version. Later, you can, if you're interested, you can actually search on the web or send me an email. I can share you a preprint. So here are just the two examples. Again, we can use the self-harm as the prediction objective here, E950. Okay, so in this network, in this visualization, each node represents a diagnosis. So the red one represents the risk we want to predict, right? So here we try to predict the risk for self-harm, and the red, the black dots represents the diagnosis or diseases that this patient didn't get before, and the orange or yellow dots represents the diseases that this patient already acquired. So you can imagine that for each patient, we can create a personalized comorbidity network because all those different patients, they have a different records in the past. So for this patient, we just randomly pick one from the data. This patient already have two diseases, and we consider this patient with a very high risk. The first disease is 242, which is some thyroid problems. Because we are not a domain expert, so at first we thought it was weird, but after did some literature review, I found it turns out to be like the thyroid. This thyroid problem has something like hormone disorders, which may lead to self-harm behaviors. So this makes sense, right? This is the biological process. And the second, 303, this is the alcohol dependence syndrome, right? So you see that the second one is actually more behavioral related. So although 303 does not lead to self-harm directly, but it can lead to, say, for example, 291, which is the alcohol-induced mental disorder, right? So this makes sense. So alcohol dependence syndrome leads to these related mental disorders, and this mental disorder leads to self-harm and suicide behaviors, right? And another possible path is through the 038. This is like another disease, right? So you can observe that on each path we have a probability, right? So in general, in our new model, we can explicitly calculate the risk propagation path, for each patient. So for this patient, when we tell the healthcare professionals that this patient has a chance to kill himself or herself, this is how we make the prediction, right? So because there is there's a chance to get some biological hormone disorders to the self-harm and suicide, and second, this guy's behavior is also not good, right? There could be two paths that lead to self-harm eventually. So this is really exciting, and in our paper, in this, the first paper is a psychiatry journal, but the second paper is more methodological journal. So in this IEEE journal, we apply it to not only self-harm prediction, but also 4 different types of diseases. this is heart failure. I believe there was another COPD. And the fourth one, I kind of forgot, but something like a tumor or cancer. Okay, and it all worked very well. Okay, and then I have like 5 minutes left. I want to quickly introduce a second study, which sounds totally different from this, but actually the model was really similar. So the second study is to predict the suicide risk using knowledge graph, and the data is totally different. The data here is from a service called OpenUp. So it is a free online mental health consultation platform for 724 hours, and it is provided by a Hong Kong Jockey Club. Basically, whenever you have any mental troubles, you can get help from real person, from the real, very well-trained social workers through social media. It could be Facebook, it could be Instagram, or it could be WeChat. Okay, and this is actually the largest of its kind in the region, especially among the Cantonese speaking users. And this is a screenshot of the synthetic data we created. We try to mimic a real world conversation because we have to protect the privacy of the real conversations. But in general, it's similar. It's like we have counselor, and we also have a help seeker. And counselors will do some introductions and try to ask questions and try to provide help, provide accompany, and provide suggestions to the help seekers. So in general, we try to reduce the risk. And at the end of the conversation, at the end of the service, the counselor would have to provide a risk assessment for this help seeker, whether this help seeker has a risk level for committing suicide. And if so, we can provide additional support, right? We can have some follow-up phone calls, or we can talk to this guy again on social media and others, right? But the problem for OpenUp is that first, making this judgment is really subjective, right? It's up to individual social workers. And the second, the social workers actually come in and go. So there are always some newcomers who didn't have too much experience. And according to our secondary data analysis, the newcomers, their performance was actually really bad. So what we try to do is that we want to have a AI assistant, which can provide the risk assessment automatically for the social workers. So basically to provide a second opinion, right? In case the real person made the wrong decisions. So if there are some conflict between the machine, between the model and the real person social worker, we can, for example, we can introduce another person to give a final rating for this case. So here we are dealing with the free text, right? So you might imagine that we are dealing with the data that is totally different from the structuralized EHR data in the first study, right? But actually we use similar approach because we are dealing with human language, and human language is really complex. Especially here, we're dealing with the Cantonese content for suicide. So the difficulty that first, you might have heard a lot of this good news about using natural language processing or AI or chatbot for all kinds of applications, right? But first, most of these applications were for English or Chinese Mandarin or Japanese, right? So those very well done models were mostly built up for those popular language. But here we are essentially working with Cantonese, which is only, I mean, it's the dialogue of Chinese, but it's quite different from the Chinese Mandarin. So we actually don't have a very well trained model for this in the first place. So essentially we have to build our own model on top of a Mandarin version. Okay, and the second, this is for suicide. So it is highly domain specific. So you can imagine that it is much more difficult than predicting like whether this guy is a girl or boy, or whether this guy is going to buy this product or not. So it's very delicate. I mean, there are a lot of the subtle features and subtle topics that we have to capture. So that's another difficulty. And the third is about the data amount. So here we are dealing with nearly 10,000 such conversations, which actually represents one of the largest in research domain. But as compared to the general natural language processing, the data is still not enough. For example, a popular language model, the BERT, proposed by Google, I guess, the BERT model itself has over 1 million parameters. So you can imagine that a model has over 1 million parameters. So how much data you need to train a model, right? So the model itself was trained on by Google, by Wikipedia and all the encyclopedia and all the books in the data set and others. But here we only have nearly 10,000 such conversations. So although it is large of its kind, but it still, it doesn't represent the sufficient information to train the model. So in ideal world, we have unlimited data and we have unlimited time to train the model. So we can just through a deep learning model, and eventually in the model, we will learn the patterns. But here we don't have the such data and the time. So the solution we try to address it is that we work with the frontline social workers to translate their domain knowledge into a knowledge graph. So which is the network I present here. This is a knowledge graph. It represents the domain knowledge. In the past, the domain knowledge was unstructured, right? So it is hidden in those social workers. But here we translate it into a knowledge graph, which is computer processable. And the next step, we'll get back to the first model. It's like we have to try to translate the topological properties of this knowledge graph into a latent feature vector. And then we can use the feature vector to predict if this person has a crisis level for committing suicide. Okay, so this is a general idea. And so basically it gets back to the network embedding, but this network is a knowledge graph, so it is actually more sophisticated. Also, by the way, this is an English translation. The original one was Cantonese, Chinese. So you can see that we have multiple items, the keywords. For example, you can see that here, parents, father, boyfriend, sister. So those are all about family members, right? And here DSE. DSE is basically like SAT in the US. Studies, schools, midterm, homework, graduation, right? So those are all about academics. So basically, through working with social workers, we identify those different groups of keywords. And then the edges are the most sophisticated ones. So each edge represents one semantic relationships connecting these two terms. So here in the first study, the edge only represents the comorbidity frequency, but here the edge represents the semantic relationship. So it's not only a relationship, but it comes with the semantics. So that's why we have different colors, because we have different semantics described by this knowledge graph. Later, I'll give you some examples. And in general, the model follows a very similar approach, right? We have this knowledge graph, so we have to embed this semantic information into the language model we have. And because they are human language, it has a sequence, right? So we have a LSTM module to combine all the words together. So eventually for each help seeker, we can generate a risk assessment, okay? And I'll give you the example here. This is the embedded results. Again, only use 3 dimensions to demonstrate the idea. For one thing, the location of those items, similar to the previous study, they represent their semantic similarities, right? The closer the distance, the more similar semantically they are in human language. But the more interestingly is that here, the directions or the angle of the edges connecting those different terms actually indicate the semantic relationship. So for example, here we only consider the purple ones, right? Get back to work may lead to unhappy. Break up may lead to becoming friends, right? Failure lead to suicide, talk lead to comfortable. So in general, you can see that these purple edges represents may lead to relationship, right? So it is a relationship and it comes with the semantic may lead to. And you can observe that those edges are largely parallel in this semantic space. Okay, and similarly, this light green, turquoise colored edges is opposite too. So confident is opposite to unhappy in general, right? Dating is opposite to breaking up, right? Work is opposite to comfortable, right? For the majority of the population. But in general, you can see that those similar colors, they are largely parallel. Okay, so the beauty of this embedding is that the location, the distance between terms, between those keywords, represent the semantic similarity, just a similarity. But the angle of those edges actually represents the semantic relationships. And when we try to optimize this embedding, we basically try to achieve both objectives together. We try to make the same semantic relationship as parallel as possible for all these for all the edges of the original network. So this is the three-dimensional space. And similarly here, we use the blue dots to represent the help seekers who didn't have the crisis level. And we use the red triangles to indicate the help seekers who are with the crisis level of suicide. And similarly, for only three-dimensionality, we can differentiate quite a lot, but not everything. And eventually the model, the final model has over 100 dimensions. Okay, and this is the results. Similarly, the C statistic is high for both, but that's mostly because the negative cases were largely accurate, right? So we focus on the positive cases. For precision, again, improved a little bit, not too much. And for recall, that we actually improved it quite a lot. It's improved from less than 80% to nearly 90%. So this is the good performance of the model. And currently we're working with Jockey Club and trying to implement our models in their system. So with more conversations, we can provide a dynamic risk assessments and provide such a real-time decision support for the help seekers. Okay, so that's it. I run a little bit over time, but I hope that we still have some time for Q&As. Thank you so much for the chance to present my work here. Thank you very much.
So thank you. And so the slides and the video will be available on the Big Data Health Science Center web. And now is the question and answers. So if you do have any question, not quite sure how the format will be. Can they just open their link and answer the question directly? Or
if anybody has questions, you can use the raise hand feature. I believe it's located next to your name in the chat feature, or you can just type your question in the Q&A box that you can find at the bottom of your screen. And we have a question from Edward. He asked, will there be a preprint of the paper on our website?
I can provide preprints for both for all these papers.
Thank you.
Yeah, the second paper is in a minor revision for social science and medicine. Actually, all of these papers should be published this year, but I can provide the preprints. I can send it to Miranda. Yeah.
So yeah, I can ask one question regarding to the weight you talk about in your both projects. the first one you use so you say you use the frequency of the comorbidity to design that the weight of the edge. And second one, you incorporate some sentiment there. So I'm not quite sure for the first one, you mean the frequency of the comorbidity, because as I think if they are co-currents, so that should be just a one, or you will design the double visit or frequent visit of the same comorbidity. So I'm not quite sure how to design that edge in the comorbidity network.
Thank you very much for the question. Yes, so we use the frequency. So on the edge, the network is a weighted network. So the edge has the weight, and the weight is how many times we observe such comorbidity among all the patients. So the thicker the edge, the more frequent these two diseases co-occur on the same patient.
Okay, got you.
Yeah, so this is how we define it. Yeah, thank you. And of course, I mean, because there are always some very rare cases of all the different types of combinations. But but for some edges, for example, if we only identify less than 10 occurrence, we just ignore it, because that could be just by chance instead of the actual comorbidity patterns.
Okay, thank you. So I think we have the question in the Q&A. So not quite sure whether you can see the Q&A. The question is that
I cannot. Yeah, I tried to click it, but it didn't pop up. Yeah.
So yeah, he's wondering that have you considered the unbalanced structure of the data, and did you apply any strategy to deal with the unbalanced issue?
Yes, the data is actually extremely imbalanced. So that's why here, I mean, for the risk samples, for the selection of the counterparts, we use a ratio of 1/20. Because the real ratio is much smaller than 1/20, so we oversample those counterparts when we train a model. Otherwise, the model will consider all the risk samples as noise. So basically, yeah. So we have to do some oversample from the. No, not oversample, but the downsample the counterparts when we train the model. So this is how we address this problem.
We have another question from Suda, who is going to be able to speak now.
Okay, so my question is that this depends very much on the number and the accuracy of documentation in the EHR. Like there may be several diagnoses that providers or whoever is documenting repeatedly keeps documenting, such as diabetes and other, routine things they may keep on repeating. But there may be some diagnoses, and further there may be some diagnoses which have become which have stopped happening to the patient, but just because it is a chronic condition, they may go on repeating in every subsequent visit. And so is it that the waiting process may actually be not so accurate relative to the actual reality? So have you tried to give some correction factor to account for documentation bias for certain diagnoses and not for the others?
Yeah, thank you very much. Thank you very much. It's actually a really good question. So we indeed observe this. So when we actually construct this comorbidity network, the frequency is actually the count of the patients instead of the actual number of records. So this is how we try to, I mean, because for the chronic conditions, these comorbidity patterns may occur multiple times, but we try to use the number of patients to actually calculate the weight for it. And for later, for this modeling approach, we didn't actually consider the reoccurring of certain diseases here. So yes, you're right that for some patients, especially elderly people, hypertension or diabetes, it can occur a lot of times. Yeah. But when we actually train a model, I believe that we used the previous certain number of admissions. So if the person has say over 100 admissions, actually I believe that in our data we found that some patients is over 100 or over 200 admissions in the past. So those patients, we consider them as outliers, and we only consider the most recent few admissions in the past. But I guess that you are right that we should actually introduce, say, another parameters to try to normalize such over exposure to certain diseases. Yeah, thank you very much for the suggestion. Yeah.
So we do have another question from the chat box. So can you explain a little bit about the difference between the DEX to VAC method and the other clustering method in exploring the comorbidity pattern?
And other clustering methods. You mean tree analysis? Yeah, we didn't use tree. You mean decision trees or something like that, right? So DEX to VAC is an embedding method. So the decision trees or other classifiers or clustering methods, they are something here. So the classifier here. So in this paper, the classifier was the deep neural network, but we can replace this with the, for example, decision trees or logistic regression or Bayesian classifiers or any other classifiers here. But DEX to VAC is basically an embedding method that try to learn a latent feature vector which can represent the patterns of something. So here in this case, DEX to VAC represents the comorbidity patterns of the multiple diagnoses and multiple admissions of the same patient in the past. So it basically try to translate that into a new features, right? Because previously, if we consider all the possibilities, that could be over 100 million features. But here we try to reduce it to 64 such latent features, and we can use those features as the input of the classifiers. And we call it the latent features because this process is a black box. It's a black box model. So for this 64 dimensions, for each dimension, we actually mathematically we don't know what is represented by each dimension. But post hoc or secondarily, we probably can get back to examine what each feature represents, but mathematically we cannot guarantee that. So in general, the short answer is that DEX to VAC is trying to learn high dimension features into and translate that high dimensional features into a lower dimensional feature vector. So it is not a classification method. The classification method or classifiers is actually the very last step of the model here. Yeah, thank you very much for the questions.
We have another question from Dr. Sean.
Hi, Qingpeng. I really enjoyed your presentation on very interesting projects. I'm not the big data expert, and so maybe forgive me if I ask stupid questions.
No.
For the second project, I didn't quite get well about the directions of the several terms. If you can, yeah, I think this slide. So, so in your model, you considered both directions between the two terms, assuming in parallel, and also it's the direction of those like the pairs of the terms depends on the the calculation of your model, or you define these directions before you run?
Yeah, thank you very much, Dr. Chow, for the question. Yeah, it is actually a little bit tricky to understand for non-technical readers. So basically, this picture is actually in a supplementary material, so not in a main manuscript. So in general, it's like, for one thing, we have this network, right? And this network is apparently very complicated. And here, for this example, we try to use only 3 dimensions to represent the full information in this network. So there are 2 objectives. First, for example, father, parents, or others, because they are close, topologically, they are close, right? The network distance, which is basically the number of edges connecting, of the paths connecting them. If they are directly connected, the distance is 1. If say this one and this one has to be connected by another node in the middle, so the distance is 2. So among those nodes, first is the distance, right? So the distance is translated into the distance in this 3-dimensional space. So it is not a topological distance, but it is an actual physical distance in this 3-dimensional space. So this is the first thing. The distance is translated into distance. Okay. And the second is that, I mean, for the first study, because all the edge has the same semantic meaning, it's co-occurring, right? So we don't have to care about the angle connecting those different edges, different terms. But here, because we have different colors, different semantic relationships, so we hope that the same semantic relationships connecting 2 nodes, the angle should be similar. So the angle of the same semantic relationships, they should be in parallel. So this is the optimization objective. So you can imagine that we start the algorithm at some random location of those different terms, right? And we can calculate the angles and find that, for example, this angle is here. So for example, originally, this angle is here, and the angle between dating and breakup is here. Okay, and we can calculate the angle difference, and we find that we hope that the angle difference is 0, right? But because it is not 0, so the next step, we flip it, we change it a little bit, so we find that the angle is smaller, and then we try to calculate it, try to change. So basically, you can imagine that there are many hundreds or thousands of those angles between those terms. And for each iteration of the model, we try to reduce the aggregated angle difference. So eventually, when the model converges to a solution, it comes to something like this. It's like the same semantic meaning lead to parallel angles connecting those related terms. You can see that here. This is insomnia and sleep. They are opposite to each other. And dating and breakup, they are also opposite to each other, right? So the distance, represents the topological distance in this original network, and the angle of this edge represents the color of this edge, or the type, the semantic type of the edge. So yeah, I'm not sure whether I explained it well, but in general, we use the location and the angle connecting different nodes to represent the semantic and the topological relationships between those different keywords in human language.
Okay, I got it. So I guess so it's still based on the calculation of your model, like finally you set up this kind of relation.
Yeah, because this one was constructed by social workers, and the model, of course, you can read it, but it's too complicated, and we translate it into this simpler form, so our computers can process it and use it for predictions.
Okay, got it. And in terms of this lower dimension vectors model, so you mentioned that you can do 3 and you can do 4. So I guess maybe there's kind of the trade-off, and how did you make a decision like which numbers of the dimensions you will use in your model? It's kind of the balanced strategy there.
Yeah. This is another good question. Actually, for those kind of deep learning models, this part is part of the black box. So we don't have a mathematical tool to analytically guarantee that how many dimensions is the best. So we don't have the mathematical guarantee for that. So in practice, we have to try it out. So in general, we try the n powers of 2, like for example, 16 dimensions, 32, 64, 128. So basically, we just try it, and then we use the accuracy to determine which is the best. And of course, in the paper, we could do some sensitivity analysis and demonstrate that for a wider range of the number of dimensionality, the model can still perform reasonably well. But here we don't have math to prove it.
Okay, got it. Another quick question. You mentioned that in your project too, you worked with social workers and other domain experts on trying to translate the domain knowledge to knowledge graph. So what's the procedures looks like, and how did you work together?
Yeah. So it is actually quite time consuming. Because at the beginning, we got the data and we tried some traditional machine learning models and find that it was not quite predictive. So then we talked to those the leaders of the social workers, and first we do some analysis of the data. So we extract those popular terms in the conversations, and then we ask the social workers to provide additional terms that they think are important to the prediction, but were not included in our list. And then, so basically, this is the seed of those terms. And then we asked them to sit down for multiple days and try to manually screen out those terms. And whenever they find that there is a semantic relation, for example, taking drugs may lead to something, right? Or for example, sleepless may lead to taking whatever drugs or sleeping pills, and then they mark it in an Excel file. And basically, of course, before we start this labeling approach, we sat down together to actually to write the data together, and then we have a common sense. We have a common pool of the semantic relationships, and then we ask the social workers. We split the data into different parts, and we ask the social workers to label it. So in the initial part, in the initial set of the data, each edge was only labeled by one social worker. I understand that it could not be the most reliable. So later on, we employed another set of social workers to go through them again to make sure that it is valid. And this, you can imagine that this knowledge graph is ever growing. If we identify new terms or new semantic relationships, we can always make changes here.
Yeah, it's kind of like interactive.
Right. So the only thing is that we just have to retrain the model a little bit. Because we are receiving a lot of more conversations, especially during COVID-19, we have accumulated quite a lot of new conversations. So we can update this knowledge graph and retrain it using new data. So it's ever growing. Yeah.
I think we have time for one more question from Suda, and then we'll let you go to bed.
Okay.
Mine is a very short question. or request, because, you know, I'm definitely not from machine learning or statistics field. If it is okay with you, we would appreciate if you can allow this PowerPoint to be distributed to us so that we can read it slowly and kind of get more based on what you have spoken. Thanks a lot.
Sure, no problem. Thank you very much for your interest in our work.
Yes, all of this will be available on our website, which I'll post the URL in the chat, and I'm sure you all have access. Okay, there we go.
Okay.
Thank you so much, Dr. Zhang, again. And it was so fascinating. I'm just blown away by every seminar we have. To the attendees, thank you again for attending. There should be a survey that pops up when we're finished here, and we would appreciate it if you took just 5 minutes to fill it out and help us plan our future seminars.
Okay, yeah. Thank you very much. Have a good day.